whole load of standard integrals here. Remember these guys? And you have to memorize them. So I'm going to give you a quick quiz. I'm not going to put you in any, I'm not going to pick in somebody. That wouldn't be fair. But I'm randomly going to pick some, and you're going to tell me, a volunteer is going to tell me what the antiderivative is. Okay, what's the antiderivative of secant tan? Just share it out if you know it. Secant tan, antiderivative.
Secant plus C.
Correct. Oh, well done. I forgot about the plus C. Nice baby one. E to the X.
E to the X.
Plus C. Okay. Secant
Plus
squared.
C, of course.
Yeah. Secant squared.
Tan X plus C.
1 over the square root of 1 minus x squared.
Arc cosine?
Almost.
Arc sine.
Yeah. Or inverse sine, as I would call it. Last one. Ugliest one of the lot. A to the power of x. Antiderivative.
A to the X over natural log of A, I think.
You are correct. Plus C. You got it. I mean, if you can memorize these, it just makes your homework go quick. So see if you don't you have to kind of, oh, God, is that one, right? And it just slows down the thought process as well. So put some time into it if you can. Get these guys going. So here are some examples. We're basically practicing indefinite integrals, right? The ones with the plus C's on it. So talked a little bit about these yesterday, but I thought we should take them a little bit further, actually sort of do them. In this question here, whoops, there we go. In this question here, it's a power rule. We do not care what that is. It's a power rule, right? X to the power of 2, X to the power of half, X to the power of 1.2, they all count. So add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power plus C. Now, there's nothing really that I need to do with these 3.5s and 2.2s. The reason I don't need to do anything, according to style points, if the original is decimals, shouldn't these be decimals? So I don't change anything. Is there something better I could do with 4 over 2.2? What could I do?
You can make it into a fraction that doesn't use a decimal, but I currently don't have my calculator on me, so I don't know what that is.
It's 20 over 11.
Okay, so there you go. And then you hit, remember the little shortcut, math number 1. There you go. And the second one, 3 divided by 3.5. And we'll do a math on that. And number 1. You see how the calculator can, can turn things into slightly prettier looking answers. I don't think that's the prettiest looking answer in the world, but that's kind of as pretty as it's going to get, right? Are we comfortable about that question then? It's really just a power rule with weird decimals and what you don't need to fix and what you should try and fix. Here's the next one. I get deja vu in this. No, I don't think we did it. I did it with my, I think I did it with my evening class. Have we done this question yet? Don't recognize it?
I think we went over this kind of with our homework, but we didn't actually do the question.
Okay, so at the end, I kind of talked through some questions. I remember doing that. Yeah. So I'm kind of going back to the ones or some of the ones I talked through and doing them a little bit more. Now in this one, I'm going to distribute 2 secant times that gets me 10 secant squared t. And 2 secant times that's going to get me 4 secant t tan t. Now that is a good thing to do in this question because I know the antiderivative of this guy. Anybody want to tell me what the antiderivative of 10 secant squareds is?
N tan x.
And what about 4 secant tans?
Four secant t.
Now in this question, it's plus c. Well, let's suppose it was that guy. Same question, right? So imagine I just went to this line. Then it would be 10 tangent t again, plus 4 secant t, evaluated at x equals 0 and finishing at x equals pi upon 3. This pen's kind of dying out. I think I'll move on to this pen. What do we get then? Well, we get 10, the tangent to pi upon 3, plus 4 secants the pi upon 3, take away 10 times the tan is 0, plus 4 times the secant is 0. I know, because I've scanned through the homework, that there are some questions in this section and the one before it where you have to find the exact value of sines, cosines, secants of standard angles, pi upon 3, pi upon 4, pi upon 6, and so on. So that one there requires, this one in particular, requires this triangle. You can do it with a unit circle, and if you're used to that, that's totally fine. In this triangle here, that's what we've got. Now, if I want to find, for example, the tan of pi upon 3, I look at this angle and I say, okay, you're the opposite and you're the adjacent, and the tangent is opposite over adjacent. So that gets me 10 times root 3 over 1. Plus 4 times. Now, if you want to find any of the reciprocal ones are secant, cosecant, and cotangent. You can still get them. There are 2 ways to do it. One is you just memorize the formula, and the other one is that you just recognize that it's the same thing as the reciprocal of the cosine. So I'm going to find the cosine of pi upon 3. And the cosine is adjacent over hypotenuse. So it's essentially a half. And isn't the secant then the reciprocal of that guy, which is 2? So 4 times 2. Now, any angle, let's rephrase that. Any number that happens to be 0, pi upon 2, pi upon 4, do you know those kind of ones that are exactly on the boundaries? Do you know you can get the answer just by doing the calculator, because they're always going to come out as 1s and 0s or undefined. 10 tan zeros is 0. And does anybody know what 4 secant 0 would get you if you used your calculator? Which would be 4 times 1 over the cosine of 0. What number, and it is a number, is 4 secant zeros?
Is it 1?
Yeah, so 4 secant zeros gets you 4.
Yeah.
Yeah. So this guy becomes 10 root 3, add 8, take away 4. And so this guy becomes 10 root 3, add 4. And that is the answer. That's what you type in using WebAssign. Hopefully you've had experience. Do you know if you click on WebAssign, a little thing appears on the right-hand side that allows you to do fractions and square roots and things. So you will use that to set that up. Do not turn that thing into a decimal. And one of the things that concerns me about these types of questions is that you might do all the hard stuff correct, and then you just kind of don't get this number right. And so you keep getting the wrong answer, and you think you don't know how to integrate. That's not the problem. You did know how to integrate. What you don't know how to do is find the exact value of tan pi upon 3 or whatever it might be, right? You wrote down the wrong number or something. That's kind of where it can go wrong. If you like using that right angle triangle guide, that's how I would use it. If you want to use your unit circle, that's fine as well. Maybe you should get a printout of your unit circle and have it stuck somewhere near this group of homework questions so that you can refer to it when you need to do it. Of course, if you give me numbers, isn't it a definite integral? If you leave it blank with a plus c, it's an indefinite integral, right? Remember, there's a slight difference between those two. Right, next one on my list. Slightly different question. It's basically question 5 from the homework. We're being asked to check, is this true? And they tell you by using differentiation. Well, if the antiderivative of cos squared x is this, then shouldn't the derivative of this be cos squared x? You see, I'm basically just working backwards. So I'm going to call this guy y. And here we go. If you differentiate this guy, a half x gets me a half. If you differentiate 1/4 sine 2x, you get 1/4 cosine 2x. Oh, don't you get times something else because it's a general? What else do you get? Times general?
Times 2.
Times 2. So what I'm looking at here is 1/2 plus 1/2 the cosine of 2x. And that might not look like cos squared x, but it is. And so I happen to know it is because I've probably seen thousands of these blinking things in my life. But you might think, well, I don't know that that is. So this is one way to keep going. If you look through your list of identities, there's a group of identities called the double angle ones, and they allow you to change the cosine of 2x. And one of the versions of that, because there's 3 of them, is that. So I'm turning the cosine of 2x into 2 cos squared x minus 1. I'm then going to distribute. Bingo, it works. So Calc Trig, it has reared its ugly head a couple of times today, and no doubt it will, in the next 8 weeks, rear its head now and again as well. So it's, what's the issue here? There is nothing that you've learnt in math from probably Math 94 onwards that won't sometime appear somewhere else in later math. Off the top of my head, right? Quadratic formula. Who's going to use the quadratic formula again, right? You probably haven't used it for months, maybe 6 months. I haven't seen a quadratic formula, never needed to do it in any calculus questions. I can guarantee there will be a question in the future, not necessarily this class, but definitely in the future, where you have to use it. Isn't there things in trig? You have to be able to use them, right? They're going to be factoring. God, factoring never goes away in math. Don't you factor all the time, all over the place, right? So all those skills that you've picked up over the years, over the classes, don't stick them in a little cupboard and lock the door and say, that's it. I've finished 141. I got my 3.5. I'm happy. Close the door. Forget all that stuff. I never need to worry about it again. That's not a good attitude because you are going to use it again. Okay, let's look at this guy. This one has an added little question that I'm going to show you. At least my version is. That guy is 2 cosine x. And that guy is e to the x plus c. That was dead easy, right? That wasn't the problem, right? Antiderivative, boom. It then goes on and it gives you 4 pictures. And it says, use various versions of this, and which one of these would represent it? So I'll show you what they mean. What I've done here is I have put, oh, nobody noticed. That's what I did. It's negative 2 cosine, right? I have put negative cosine, 2 cosine x plus e to the x, add 0, add 2, add 4, add 6. In other words, replace that with, oh, anything you like. Add 1, add 2, add 3, add 4, right? And if you draw some pictures, that's what you get. And so when you do your version of this question, take this equation, replace it by 0, plug it in as y1, replace it by 1, replace c by 2, replace c by 3, and then draw a picture. And look at your picture, and one of your 4 choices will look like that, and you'll say, yep, that's my guy. I'll pick him, right? So that question kind of now makes sense to you if you haven't already done it.
So
Hopefully when you see it.
my graphing calculator is Desmos.
Okay. So you will type in 4 separate functions. Desmos allows you to draw more than one graph.
Yeah.
So just plug it in 1, plug in 2, plug in 3, plug it in 4 times. So you'll have 4 distinct functions. They'll probably be different colors as well, and you'll get the same effect.
Okay, cool.
Okay, so Desmos works fine. Any questions, or are we good? Last chance. We good? Moving on. Oh, God, I didn't realize we'd almost covered this. This is good. We're going faster than I thought we would go. The last piece of work are going to be questions that are applications, which is, let's use integrals to do some stuff, right? Let's use areas under curves to do things, right? So here's an example of an application. The acceleration of a moving object at any given time is given by that equation. So we are going to model a moving object whose acceleration changes through time. Now that's a bit more advanced than the usual question. Don't you normally get questions, this car or spaceship has an acceleration of 20 meters per second squared, right? It's a fixed number. Can you see here at the 1 second mark and at the 10 second mark, the acceleration is changing, right? It's different. Right? You're also told in this question that the velocity at the beginning at time 0 is 4. And you're also told that in this model, we're only looking at what the thing is doing in the first 5 seconds of its life. So this is the acceleration of this moving object for the first 5 seconds of its life, and the velocity at 0 is 4. And from only that question, from only that information, we can answer these 2 questions. The first one is, find the velocity function at any given time. In other words, what is the speed? I'm using the layman's term. What is the velocity of this moving object? And question B is, what distance does it travel in the first 4 seconds? That's interesting. Okay, let's solve it one at a time. Before I talk about solving that, let me tell you something from Calc 1 that I'm going to use. Can you remember you take the displacement function? And can you remember what happens when you differentiate the displacement function? What do you find? Can you remember? You find the velocity function, yeah. And what do you get if you take the derivative of that, which is essentially the derivative of the velocity function? What do you now get?
Acceleration.
Yes. Can you remember a couple of questions you probably got in Calc 1 where they said the position function is t squared plus 2, what's the velocity at 4 seconds, what's the acceleration at 5 seconds? Can you remember finding derivatives that tell you that? Essentially it's saying the rate of change of position with time, that's what a derivative is, a rate of change, is the velocity, and the rate of change of velocity with time is acceleration. So I'm going to use that, but I'm going to use it the other way. If I know the acceleration and I would like to get to the velocity, what do you think I do with the acceleration? If going this way is differentiate, what do you think, what process would be working backwards? Differentiate, working backwards.
Integration.
It is. So back to my question then. How does that help me to do this question? Well, if I want to find the velocity function, don't I just do an indefinite integral? I integrate it. And when I integrate it, add 1 to the power, take away 6t, that's fine. Oh, plus c. Right? When you do an indefinite integral, you always have that plus c tagged on. But can you remember this piece of information over here that you were told in the question? How is that piece of information going to help me to find c? How would I use it to find c?
If you make the t's 0, then c has to equal 4.
And 0, 0, 0, and c has to be 4. So I have now answered question A. The velocity is 2t squared, take away 6t plus 4. Isn't that cool? Now, question B asks us to find the distance in the first 4 seconds. Well, you know, if you take a velocity time thing, isn't the area underneath the distance traveled? So if I want to find what's the distance traveled in this velocity function during the first 5 seconds, the distance traveled is the integral from 0 to 5 of the velocity function. So it's going to be the integral from 0 to 5 of that guy. And I'm just going to dot, dot, dot that. Can you finish it off yourself in the usual way? Do you see how we can actually create models for velocities and position functions from only being told what the acceleration at any given time is and what the initial velocity is. That is a pretty impressive thing. Now, don't worry about the next question I'm about to do, but I want to kind of show you the power of integration. Does anybody here, has anybody here done, it might be kinematics, it might be physics. Does anybody here know what the formula for the velocity of a moving object is when it's got an acceleration of a and an initial velocity of u? Does anybody done that question knows what the formula is? Any ideas? Maybe you haven't done it yet. So, a is acceleration, a fixed number. If you want to know what the velocity is after t seconds, it's at plus u, where u is the initial velocity. Initial velocity just means the velocity at time 0, right? Well, let me do that. The acceleration is a number a. The velocity is the integral of the number a. The integral of a is at plus c. If you plug in 0, you find out c is u. And you get that guy. If you take any physics formula that you've ever been told, if you differentiate that formula, or if you integrate that formula, there is a very good chance that you will end up with another physics formula that you know. Does anybody know what the distance traveled formula is for a moving object? It's a half at squared plus ut plus s naught. Trust me, if you integrate that, you'll get that. As I said, don't worry too much about that. I'm not going to ask you that. It's a test question. But I just want to show you that this stuff is good stuff. We can use applications. Here's our next application. This one is more like a homework question. The rate of change. Right, so I'll give you a little story for it. Can you imagine that you've got a big tank and it's full of liquid, and there's a hole in that tank and out is pouring water, it's leaking out, and it's leaking out at the rate of 200 take away 5 times t. So at the 10-second mark, it's leaking out at a rate of 150, right? And so on and so forth. And then it goes and says, find the amount of water that flows during the first 20 minutes. The amount is just the integral of the rate function. So if you're ever told a rate to some kind, if you integrate it, that will tell you the amount of whatever this thing is. In this case, it's liquid. And it's during the first 20 minutes. So it's there. So this is going to be the integral from 0 to 20 of 200 take away 5t dt. And this is going to be 200t take away 5 over 2t squared from t equals 0 to t equals 20. And that's 200 times 20 take away 5 lots of 20 squared minus a whole load of nothings. So 4,000 take away some ridiculously big number that I'm about to find out. take away 1,000. And the answer is, whatever the units have to be, let's say they're cubic meters, that in the first 20 minutes, 3,000 cubic meters of liquid have left that tank. I'm not going to do the question, I'm just going to tell you the answer. If you find out how much liquid has left during the last 20 minutes, it's that. Why are they not the same? Right? The first 20 minutes, 3,000 cubic meters of water. In the last 20 minutes, only 1,000 cubic meters of water. What on earth is happening up here that is causing this discrepancy?
I guess just looking at it from a physics way, there's more pressure pushing it out and pushing down on it. So the more that there's in there, the faster
It
it'll
shoots
come
out
out.
like a bullet at the beginning.
Yeah, and of course, as
Yeah.
less there is, they'll flow slower.
So do you see this model is quite realistic? Doesn't it generate the kind of answer you would, physics would tell you to expect? Right? And it's quite a simple model, right? It's only a linear model. It's not the weirdest, yet it comes up with results that are very predictable. And in physics, they have reasons for why it's true, but you see in math, it just tells you the truth, right? And then the physics people can say, well, the reason you got this truth is at the beginning, there's a ton of water. And you know, if you got a big tank and it's full and you hit a screwdriver through it, doesn't it shoot out like a bullet at the start? But what happens is it starts getting empty, doesn't it? Kind of, right? It kind of drips out towards the end. So the rate at which the water comes out will change through time. Are we feeling a little bit more comfortable about some of these applications? Because I know not everyone is going to be a physics major, and so your knowledge of physics is limited. But really, every question I've done, hasn't it just been integrate something? So as long as you say to yourself, I'm going to integrate something, you're probably in the right place. So I'm going to show you the last question, and then we can talk about what's going to happen tomorrow. Right. And here is the homework questions. Oh, by the way, that's that question I was talking about with the plus C's in it. Do you see the pictures now? Moving on. Make this a little bit bigger. Okay. I'm not into business. I don't know what a marginal cost of a manufacturing X yards of a certain fabric means. But didn't they give me a function? And I am going to find the increase in cost if it goes from 2,000 to 4,000. Won't that become an integral? And won't it be from 2,000 to 4,000? And won't the function be 3 take away nothing 0.01x plus a ridiculously tiny x squared dx? Can you see that even if I don't know the context, give me a function, tell me where to start, tell me where to finish. Isn't that basically the end of that question? Now, how about question 14? The rate at which bacteria grow is given by 1,000 4 to the power of t. A bacteria population is 3,000 at t equals 0. So you're telling me that the population at time 0 is 3,000. And the question then becomes, find the, the population after 1 hour. Since this is the last one, this is probably going to be the worst one. And it's not going to even be nice numbers. The population at time t is going to be the integral of the rate function. So it's very like integrating acceleration gets you velocity. And it's an indefinite integral. And I'm going to integrate 1000 times 4 to the power of t. And the antiderivative of that is 1000 4 times 4 to the power of t with something left over, something I haven't added yet. Look at the bottom guy. What would 4 to the t or 4 to the x get you? What's missing?
Plus c.
The integral of 4. Well, plus c is missing, but isn't there something missing at the bottom here?
Natural log of t.
Natural log of,
T.
try again,
4t.
of, oh, 4. Darn close.
Yeah.
See, it's just a, right? 4. There aren't that many of these getting done, unfortunately. So you're probably not going to get a lot of practice at them. So you have to kind of, you know, use what you can get. Now, you're told that at time 0, there's 3000 bacteria. So P of 0 is 1000 times 4 to the power of 0 divided by the natural log of 4 plus c, and they have told me that this is 3000. Now, a lot of people think that c is 3000, and in many, many questions, c will be 3000, but not this time. Let's find out why. Isn't 4 to the power of 0 actually the number 1? So on my calculator, because there's no way I'm going to make that pretty, it's going to be 1000 times, I'll just put it in, 4 to the power of 0. That's the top bit. Divided by the natural log of 4, that's the bottom bit. And I am looking at 721.3. Add C gives me 3000. That makes C 2278.7 by subtracting 721.3 away from 3000. So there's my 3000, 721.3, and I get this guy. That means that the population of the bacteria at any given time t is going to be 1000 times 4 to the power of t divided by the natural log of 4 plus c, which we have now found out is that guy. And if the question had been, find the formula for the population at any given time t, we have now got our answer. But it isn't. They just wanted to know what's the population after 1 hour. So it's going to be 1000 times 4 to the power of 1, all over the natural log of 4, plus what c is equal to, which is that guy. And 1000 times 4 divided by the natural log of 4, and then add 2278.7, and I make that 5164. Are we good? Any questions about that, or are we good? The last chance to ask if you have a problem. Okay.